Hi there, fellow primates. I hope this video finds you well. I hope you've had a good week, like I have. I didn't work at home the entire week. I went to the museum on Wednesday and I helped interview several candidates for PhD positions that we've advertised. And it was brilliant to see that despite the hell of the pandemic, these young people managed to progress their studies up to the point of being really excellent candidates to become PhD students. The quality of them was on such a level that I think the panel members felt that if we would have been in this competition now, that we wouldn't have stood a chance against them. So that was lovely to see. Speaking of students, the museum has just put an advertisement out for a chair of postgraduate studies. So if you have ambitions in this area or you know somebody who does, I will put a link in the description. You can check it out. I think the closing date is the 18th of February. So if you want to work at the Natural History Museum, check out the link. Maybe it's the right thing for you. Now, I want to start this journal club by talking about diaries. I don't generally keep them, but when I go on holidays, I often do to allow me to remember the good times we've had. And so reading my diary, I can see that on Thursday, the 15th of May 2014, I was on a plane flying across the Atlantic to Cuba with my girlfriend Sarah and a number of our friends to go on a nice holiday there. And on this plane, I was sitting in the middle seat, Sarah was by the window, and I was seated next to a lady I didn't know who had the aisle seat. And our friend Coral was on board as well, but Coral had 1 trillion air miles, so she wasn't flying in coach, she was on the upper deck, being pampered in first class. But sweetheart that Coral is, she sent down a cheese platter and several glasses of champagne. And I remember, and I don't need my diary for this, the flight attendant coming through the aisle and stopping at our row with these drinks and these snacks. And all three of our heads went up expectingly with big eyes and smiles. And then the flight attendant said, sorry, this is not for you, to the lady in the aisle seat, and handed the drinks and snacks to us. She looked quite sad. But we were not receptive. These were our glasses of champagne because Coral is our friend and these were our snacks. So it was a lovely beginning of the holiday. Now, we are not the only creatures that keep diaries. Mother Nature, she's not a creature of course, keeps a diary too. It's not a paper diary and she doesn't write in ink. Where she writes is in the genomes of the organisms that evolve, and she writes with mutations. Now, much of what is written in genomic diaries is gibberish. It doesn't tell a story. It's just a record of the more or less random ticking over of the mutational clock across generations. But of course, genomes record much more than that. They also record the aftermath of life and death situations, of clashes between mortal enemies, of struggle in deep time. And today's journal club highlights one illustration of this, and this is about the struggle between primates and venomous snakes. Now, I want to start with a paper that was published early on in 2021. The first author is Taline Kazandjian. She was a PhD student at the Liverpool School of Tropical Medicine, and she was heading a team of researchers. The senior author is Nicholas Casewell, who was a supervisor at the Liverpool School of Tropical Medicine. And they wrote this beautiful paper that made the cover of Science, looking into the evolution of venom in cobras and comparing the venom of spitting cobras to those of non-spitting cobras. I'm going to not discuss this paper in detail, but what they found sets up the rest of today's story very well. So here, this image shows a phylogenetic tree that depicts the relationships between the major groups of cobras and a profile, a transcriptomic profile of their venom composition. So if you look at the top of the figure, you can see African cobras, spitting cobras in the upper right and non-spitting cobras in the upper left. And at the bottom left, you can see Asian spitting cobras and Asian non-spitting cobras, and another African snake at the lower right, which we shall ignore for the moment. Now, long story short, spitting has evolved in cobras 3 times independently. Once in Hemachetus, this is the taxon in the lower right, which we shall ignore. Once in the African cobras and one in the Asian cobras. Now, if you compare the venom of spitting and non-spitting cobras, you find some distinctive differences. And what Taline and her colleagues found is that if you look at these little pie charts that show the profiles of the venoms, the spitting cobras have an orange pie slice that is much less prominent or even absent in the venom profiles of non-spitting cobras. And that orange pie slice represents phospholipase A2. Now that is a ubiquitous component of venoms in snakes. It is typically enzymatic. It can have many effects on the body. It can be neurotoxic, it can be cytotoxic, destroying cells and tissues. And what Taline and her colleagues discovered is that when you look at the spitting cobra venom, it has much more of this enzyme in it than non-spitting cobras. It is much more active than the enzyme that you might find in the venom of non-spitting cobras, and it activates neurons as well that are involved in pain production. So what they find is the molecular basis of why it is so painful to be spat in your eyes by a spitting cobra, or also when a spitting cobra bites you and all these cytotoxic toxins go into your system. You can get not only paralytic symptoms, which is typical for snakes from the cobra family, but really tissue-destroying, horrible wounds as well. So they found that as a defensive weapon, spitting has evolved to deliver a very painful cargo to predators. What is the target of these venoms? Well, anybody knows, well, spitting cobras, for instance, spit at humans when they come too close and feel threatened. And Taline and her colleagues found out specifically some details about this that were suspected but never proven to such a degree. If you look at the numbers on the internal branches of this tree, and you don't have to look at specific ones, they're quite small, they estimated the divergence times of these groups of snakes, including an estimate for the origin of African spitting cobras and Asian spitting cobras. And they found that African spitting cobras evolved around or started radiating around 6.5 million years ago, just after the lineage that leads to us, humans, split from the lineage that leads to the living chimps, the bonobos and the common chimps. And the origin of the radiation of Asian spitting cobras was a bit later, and that was around the time 2.5 million years ago or so that we think Homo erectus arrived in Asia. So they make an argument that spitting in cobras evolved possibly, maybe probably, as a defensive mechanism against the arrival of strong, large, bipedal, smart, bloody aggressive primates that use intelligence and tools like sticks and stones to basically reduce the reproductive fitness of the receiving snake to zero, killing snakes. So this is a beautiful illustration of when you browse the genomic diary of venomous snakes, you can see the imprint of the actions, the mortal battles they must have had with primates that evolved in the same environments as they did. Now, is there evidence in the behavior of modern humans that something like this was going on? Vice versa, snakes have in their genomic diary the imprint of this interaction. Is it true that if you look at primates, you can see evidence of this interaction in evolutionary time? And the answer is yes. And a very obvious one is represented by this gaboon viper skull. This is actually the skull that belongs in a decapitated snake head that we have in the collection in the museum. And in 2014, I hosted some visitors from a pharmaceutical company, and I put that snake head on a table. And I remember one of the visitors walked into the room, literally stopped in her tracks, backtracked into the hallway and refused, flat out refused to go into the room where that snake head was in a closed jar of alcohol. I explained to her, this is not going to bite you. She understood that. She said, I can't deal with this. She was mortally afraid of snakes. And she isn't alone. Humans are, even in modern societies like the UK or the Netherlands, mortally afraid of snakes. People did a poll a couple of years ago of about 2,000 Dutch people between the ages of 18 and 93. And they found that Dutch people are much more afraid of snakes than they are of injections, or the dentist, or heights, or blood, or even physical trauma. So you can see that there is something in our constitution that can trigger very easily a fear of snakes. So a very long echo of an interaction of primates evolving in the context of dangerous venomous snakes. And now, how dangerous can this be? How often would there be in a traditional society encounters between primates and snakes? Well, very often, depending on what communities you look at. For instance, if you look at this beautiful book, I don't know, The Sunshines of it, by Jared Diamond, The World Until Yesterday. It's a really fascinating look at how non-modern societies, non-westernized societies do things, that no matter where you look, in the old world, in the new world, in areas where venomous snakes occur, many accidents are due to snake bites. And it can be extraordinary. If you look, for instance, at the Ashi people, an indigenous group of people from Paraguay, 6% of the Ashi die of snake bite. And this gets even worse when you look at the mortality of male Ashi. They are hunter-gatherers, and the males spend a lot of time in the forest hunting and foraging. 14% of adult Ashi males die of snake bite, and even more, of course, have morbidity, afflicted limbs, all kinds of problems. So the pressure on reproductive fitness of snakes in certain environments on humans and on other primates can be non-insignificant. And you can basically ask the question, can you see this like with the snakes? Is there evidence of this in the genomic diary of primates? And the answer is yes. And this is the paper that I chose specifically, and it is written by another PhD student, Richard Harris from the University of Queensland. His supervisor is Brian Fry, also from the University of Queensland, and their co-authors Anna Nakaris from Oxford Brookes University. And they published this really cool paper about the interactions of snakes and primate, but from the primate perspective. So taking a complementary view from that taken by Taline Kazandjian and her co-authors. And what they find, let me explain this to you. First, we need to go to a little graph about where the action happens in this paper. The question they try to answer is, if primates evolve in dangerous environments where venomous snakes can exert an effect on reproductive fitness, can you see evidence of this in some of the targets of the venom? And so if you look at this schematic of the neuromuscular junction, where you can see a nerve terminus on the left coming in to a muscle on the right, and a nerve impulse arrives and that causes muscle contraction. So you see in numbers all kinds of neurotransmitter receptors and ion channels, and if you mess around with these, then you can interfere with nerve impulse transmission, and you can cause paralysis. And if you look at the little structure labeled 6, that is the nicotinic acetylcholine receptor, and I will put how you spell that up here. And that is the neurotransmitter acetylcholine that is involved in transducing nerve impulses into muscle contraction. So if you, for instance, block this transmission, you have a toxin binding to the nicotinic acetylcholine receptor so that the neurotransmitters can't activate the receptor, then the muscle can't twitch in response to a nerve impulse, and you go floppy, you get paralyzed. And that is what happens when you get bitten by many snakes in the cobra family, the Elapidae family, because they have post-synaptic neurotoxins that knock out, that block specifically the nicotinic acetylcholine receptor. We know this already. This is interesting. But then the novelty of what Richard and his colleagues did is, well, if you look at a diverse array of primates from different parts of the world, some of which have venomous snakes and some of which don't have venomous snakes, would you be able to see that perhaps in areas where snakes can exert a selective pressure on primates, that some of the venom targets have mutated to try to become resistant to the venom? A very interesting question. Has there, in other words, been some coevolution between snakes and primates? And so what they did is they made mimotopes of the nicotinic acetylcholine receptor. What is that? In simple words, that meant that they made synthetic versions of the bit of that receptor that binds normally the neurotransmitter, but it is also the target for the binding of these potent paralytic neurotoxins in snake venom. And they made about 3 dozen of these synthetic neurotransmitter receptor mimics from primates in the 5 main lineages, and you can see representatives here. In the upper left, the black-eyed lemur represents the lemurs. On the bottom, the garnet galago represent lorises. In the upper right, the tarsier represent tarsiers. Underneath you can see a New World monkey, a capuchin monkey that represents the New World monkeys, and then you can see myself and my wife representing Old World monkeys and the great apes, including ourselves. So they made 3 dozen of these mimetopes, of these mimics of the bit of the nicotinic acetylcholine receptor where snake toxins can bind, and then they went fishing with the venoms of 7 snakes. And you can see here representatives for the 2 main groups, cobras, and this is a spitting cobra, and from both Asia and Africa, and on the right a coral snake, which is a cobra family snake from the New World, from the Americas. And then they asked the question, have some of these neurotransmitter receptors evolved resistance to the paralytic toxins from snake venom? And this is what they found. And this is a phylogenetic tree with a heat map on it that shows in different colors how much affinity these paralytic neurotoxins have for the nicotinic acetylcholine receptors in these different taxa. And this is based on the venom of the Mozambique spitting cobra, which I showed in the previous picture. And I will talk you through it. What you can see here is a striking confirmation of their expectations. They expected that in primates that evolved in environments where they would be exposed to venomous snakes, that their acetylcholine receptors would evolve a certain resistance to the binding of these neurotoxins to protect themselves. And that indeed is true. The most striking of that is, if you look at the top of the tree, you can see the genus Homo panangorilla, i.e. the great apes from Africa, having evolved a very, very low affinity to the snake venom toxins. And not just they, the orangutan, pongo as well as pretty much all Old World primates, including the monkeys, in the group the catarrhines, the tarsier, and if you look at the bottom of the tree, even in the lorises, and also in one lemur. We come back to that lemur in a moment. So in environments where dangerous cobras evolve and have lived in coexistence and still do with primates, the primates have evolved resistance to their major paralytic neurotoxins. And that is a wonderful confirmation that the snakes have had an effect on the genomes of the primates too. Equally strikingly, the platyrrhini, the clade in red near the bottom, those are the New World monkeys. And yes, although there are venomous cobra family members like the coral snakes in the New World, they are generally nocturnal, they live on the ground, whereas most of the primates in the New World are arboreal specialists, so they don't come into contact very often. And if you look at the bottom as well, the lemurs are very, very sensitive to paralytic neurotoxins from snake venom, and that is not surprising because the lemurs from Madagascar evolved in an environment without dangerous venomous snakes, so they never had a selective pressure to have to protect themselves against dangerous snakes. So a beautiful confirmation that yes, it seems like primates that evolve in the presence of venomous snakes have taken evolutionary countermeasures and evolved some resistance to some of the major venom components. Let's come back to this dopey looking creature, the black-eyed lemur. It's sitting there and it looks a bit like perhaps it likes to get high. And it turns out, so Richard and his co-authors speculated, perhaps that is the case why it has reduced affinity for paralytic neurotoxins of snakes. Even though it didn't evolve in an environment where it was exposed to venomous snakes, it eats a lot of toxic foods, mushrooms and millipedes. And Richard and his colleagues speculated perhaps, well, in order to survive on such a potentially toxic diet, they needed to evolve some changes to their neurotransmitter receptors to survive. So maybe there's a story there to be explored further. I show you one other tree, and this is if you expose the same mimics of the acetylcholine receptor to snake venoms, but now in this case a coral snake from South America, or North America, I don't know, I'm not a snake expert, from the Americas, I think North America would be my guess. You can see that the African primates, especially the great apes, still have quite a lot of resistance to this neurotoxin, as does the loris at the bottom of the tree. So that shows that even snake venoms from cobra family members that evolved in another part of the world, the resistance they evolved, the primates in the old world evolved to resident snakes, confers some resistance to snakes from the same group, but it evolved elsewhere. That's a lovely story, and it shows that there's a real co-evolutionary arms race between venomous snakes and primates. However, the resistance is partial. If you get bitten, as we all know, by a cobra, there's no guarantee that you will survive. And there's a tragic story to illustrate this quite forcefully. This is the late Joe Slowinski. He was a herpetologist who in 2001 was in Myanmar, and he was collecting reptiles and snakes. And he got bitten by a venomous snake. And he got bitten by what was then thought to be a multi-banded snake, a very dangerous snake. He picked a snake up in the mistaken impression that it was a harmless snake, a wolf snake. And as you can see in this slide here, they look quite similar. Of course, not to the trained eye of a Joe Slowinski, but it was a small snake. The snake that bit him was only as thin as a pencil and about a foot long. And they are, if you look at them quite quickly, quite similar. And this website that I found from which these two pictures come, they say, well, even though they look similar, you can easily see the difference between the non-venomous wolf snake and a crate, which is a cobra family snake. Just open the mouth and look at the teeth. That's extraordinarily ill-conceived advice, so don't do that. Long story short, because I guess many of the people who watch this already know this story, poor Joe Slowinski was bitten by this snake. He couldn't even see puncture marks on his finger. It was 7 in the morning. At 8 o'clock his finger started tingling, so they sent for help. They sent some runners to go find help through the jungle. Then around lunchtime, 1 o'clock, he couldn't breathe anymore, so his colleague had to do CPR, mouth to mouth, and they had to do that for another 26 hours. And then sadly, help didn't come on time, and Joe died after a painless but potently paralytic bite of a small crate. Research that was published last year showed that it was probably not a multi-banded crate. It was actually a new crate species that bit and killed him. But that shows you the tragedy. The irony here is, and there is some irony, that one of the major neurotoxins that causes paralysis when you get bitten by crates is called alpha-bungarotoxin. That was initially isolated from the multi-banded crate, that binds the nicotinic acetylcholine receptor with such high affinity that they used that venom toxin to go fishing for nicotinic acetylcholine receptors in the 1970s, so they could elucidate its structure. So they used venom as a tool to go fishing for the neurotransmitter receptors. But Richard and his colleagues, what they did is the reverse. They made mimics of parts of these receptors to go fishing for venom toxins to see if primates had evolved resistance to snake venom. So it's a very interesting, if somewhat shocking story, because snake bite isn't fun. Now, if you find any of this interesting at all, I've got good news for you, because Richard, who just submitted his thesis, I think this month, is willing to come on my channel in the near future to discuss some of the other things that he has been fishing for. So if you like this, stay tuned. Like it underneath the video, subscribe, sign up for alerts. I hope you have a good weekend. I certainly will, because this weekend I'm celebrating my 5th wedding anniversary with Sarah. So we're going to have some bubbly and a fancy lunch somewhere in Brighton tomorrow. So I hope yours is going to be good too. I hope to see you next week. Bye bye.